So welcome to Advanced Reverse Engineering. There's homework. The homework is to turn the hexadecimal stuff here into an executable and run it. It's due. Hopefully you've all done that and life is good. Let's talk about some tools and, what's out there in the way of tools. NASM is a tool we might want to discuss. The way to install NASM is to do that command right there at the prompt on Linux, sudo apt install NASM. So sudo will make you root. You'll have to enter your password to do that. Apt is a wrapper around the package manager for Debian. Install says go install something, and NASM is the thing you want to install. If you'd like to read about NASM, you can go to the NASM home. The documentation is here, and if you want to see how it's actually built, the source repository is available right here. Right? Where is the source repository? It's on GitHub. Okay, the GNU debugger is another tool. I don't have time to go through it in depth. I usually do that in the class, but in this class I'll have to do that separately and post a video about it. It's not the only debugger out there. WinDebug on Windows and x64 debug are out there. I think WinDebug might not be maintained anymore. I'm not 100% sure. Radar 2 is a great debugger with a cryptic syntax, and Ryzen is a fork of that. It has a great debugger with a cryptic syntax, but it also has Cutter, which makes it much easier to use. When I have time, I'll put something out there. Right? The class has been shortened this year significantly. I think it's 15 minutes shorter. The 3-hour class, but we only get 2.5 hours of lecture per week. So let's go back to writing assembly. That's what we've been looking at. Let's plow ahead. And let's think about compilation for a moment. So if I write a C program like the one up here at the top, and this is a super simple program, right? It takes a single argument, int I, and it returns that result to me. If I take that and I compile it, what's going to happen is the compiler is going to internally turn it into an intermediate form. In this case, it's going to turn it into something that may look like this. So some of the same stuff is there, but you'll notice that instead of int, we now have I32, right? So we have a much more specific type. And we have these allocation things and these store things here. And then we return an I32, which is %6. So these percent things would seem to indicate intermediate values. So let's see. I want to return the input. So I return an I32, which is %6. Here's %6. It says load an I32. And what happens here is we get an I32 pointer, %4, and align it on 4. So what's %4? So let's go up here. %4, we allocate an I32 and we align it. And that's what we're gonna return whatever's there. Well, what got there? How do we ever get anything in %4? Well, here we did a store of %0 into %4. What's %0? It's that. So the thing came in, we stored it, we retrieved it, and we returned it. Wow. Okay, that seems unnecessarily complicated, but that's, there you go. The RTL is then optimized and massaged in various ways and turned into assembly. And here's some assembly that we get out. And this assembly is in the AT&T syntax, so, just take it for what you will. So here's our start of our procedure. This is a branch protection thing. And then we have the usual preamble to a function. We push RBP and we move it. We'll talk about why we do that later on. What's going on here? Well, EDI is going to hold our first and only argument by the calling convention. We're going to store it somewhere. And then later on, we'll retrieve it into EAX. We'll undo what we did earlier and we'll return. And our return value will be EAX. So this will return what we were given just in a wordy way. And then finally, the assembly gets assembled and we wind up with machine code, which we see at the bottom. So this is a process that we go through. We don't see all these pieces unless we explicitly tell the compiler, I want to see your RTL and I want to see the assembly, right? Then we can make it show us all these intermediate steps. All right. All artifacts that includes the source code, the intermediate representation, and the assembly language are useful. A lot of tools can be built up at the RTL level to do things to your program. Some program instrumentation tools will work at this level, at the RTL level. Okay. All right. So there we go. A lot of times with reverse engineering, you'll wind up seeing purpose-built intermediate representations for specific types of challenges. So let's go through more instruction set architecture topics. Zero extend and sign extend. So fun stuff. So suppose I set the lower 32 bits of a 64-bit register. In that case, the top 32 bits are zeroed out. So if I do move 17 into EAX, move EAX, 17, that actually sets RAX to 17. Okay? That's what it does. It sets RAX to the value 17 because it zeroes out the top. So we talked about how EAX is an alias for the low 32 bits of the 64-bit register RAX. Well, sort of. When I set those values, it zeroes out the top. And this is an optimization that the assembler will do for you. So up here at the top, I say, I want to put 17 into RAX. And so I assemble this and I disassemble it at the bottom, and the assembler says, I heard you. You want to put 17 into EAX. Right, this is hex 17. And I'm like, no, that's not what I meant. I want to put the quad word, or the 8-byte version of 17, into the 8-byte register RAX. Do that. The assembler will say, sure, gotcha, understand, I'll put 17 in EAX. The way to get around that is to use the keyword strict. Right? Strict says, hey, I really mean it. Put 17, 8 bytes long, in RAX. Now the assembler will do that. And here's that little weird move ABS thing that'll pop out. But we can see what's happened, right? So here's a 4-byte version of 17. The low order byte holds 17. The higher ones all hold 0, right? 17 is 16 plus 1. And here it is again, 4 bytes. Here's the 8-byte version of that, right? So we just wasted a bunch of bytes. And we notice we shifted over one because we have a prefix byte here indicating that we want to use the full 8-byte addressing. All right, so we can use strict like that. You may expect strict to always work, but it won't. So just something to keep in mind. So there is an explicit zero extended move. So when I put 17 in EAX, I zeroed out the top 32 bits of RAX. That happened without me asking for it. What if I modify BX? Do I zero out the top 48 bits of RAX? And the answer is no, I don't. That only happens when I use a 32-bit register. It's the only time it happens. Oh, what if I want it to happen? Well, there are explicit other versions of it. So for fun, if I try this, put this 16-bit value that's in BX into RAX, it won't assemble. It'll say, no, that's 16 bits, that's 64 bits, I can't do that. They don't match. If I try this, surely this will work. Nope, it won't work. And I can't do this either. I can't take the 16 bits at the address pointed to by RBX and put them in RAX. These won't assemble. But I could tell it I explicitly want you to zero extend, and then they work. And that is the move zero extend or move ZX instruction. So now I can put a 16-bit thing in this 32-bit thing, and it will zero out the high 16 bits. Same thing for the 64-bit thing. It zeroes out the high 48 bits, etc. Life is great. I come here and I say move ZX, put this 32-bit value in this 64-bit register, and this will not assemble. What? How do I do that? For the last instruction, I do this. Because this is the implicit 0 extend, right? If I put EBX, a 32-bit thing, in E, I'm writing to the low 32 bits of RAX, which automatically zeroes out the high 32 bits of RAX. I know. Everything in assembly has weird exceptions, and this is one of the weirder ones. So that may seem weird to you. There's also the problem that if I put negative 17 in a register like BX and I 0 extend it, I get the 0 extension, which is not a negative number. So I put negative 17 in here. That looks like FFEF. When I 0 extend it, it looks like 0000 FFEF. That's not right. So it'll be a positive number. What I really want to do is to extend the sign bit from the 16-bit number all the way to the sign bit for the 64-bit number. And, right, because what I have is this. The 64-bit value ends up looking like this, which is this number that's not at all negative 17. And that's not what I want. I want this number. Notice how the F's, the last one, is sort of smeared across all these others. The sign bit has been extended all the way across. And that's in fact what I can do. There is a sign extend, which is similar to the 0 extend. The sign extend, if I take 17, negative 17, put it in BX, I can 0 extend it into RAX, or I can sign extend it into RAX. This will set RAX to 65,000 something. This will set RAX to negative 17 in the 2's complement sense. That's what I want. So you got to pick. You got to remember what are you trying to do and choose the appropriate one. Like MoveZX, there's a version to move a double word to a quad word. A slightly different mnemonic exists for that. Move SXD. There's no corresponding move as ZD because that's just moving one 32-bit register into another. Right? Because then it automatically extends. Right. Now, what if I write move SX and I should be using move SXD? Well, NASM will automatically fix it. So if I write all this stuff up here, right, stick negative 17 in BX, it'll do that. Stick BX in RAX with sign extend, it'll do that. Stick negative 17 in EBX, it'll do that. Stick EBX in EAX, it'll do that. Stick EBX in RAX sign extended. I forgot the D, that's okay, it'll fill it in for me. And then if I include the D, same thing. Whew. Let's talk about system calls. So syscall is an instruction that we'll use a fair amount. It's the instruction that triggers a context switch from our user space into the kernel space to then perform some action within the kernel. So as a result, knowing how to use it's important because the kernel controls a lot of the resources we need, like memory. All right. It's the rough equivalent, if you've done 32-bit stuff, of int 80. If you've done early Windows or DOS stuff, it's the equivalent of int 21. You can read about the system call table on Chapman's blog post, and in fact, that's where I recommend you go. That first link right there. The basic approach is the following. You figure out which system call you want, and you put the number of the system call in RAX. The system calls all have numbers. Figure out which one you want, put that number in RAX. Exit is 60, write is 1. So we'll use those a lot. Load the other registers with arguments to the system call, and the order in which arguments go is shown right here. RDI holds the first argument, then RSI, RDX 10, 9, 8. You can only pass 6 arguments, that's it, that's all you get, period. Once you've loaded those in, and right there are going to be integers or pointers. Once you've loaded those in, you invoke syscall. Okay? The return value, if there is one, is an RAX. It could be a number, it could be a pointer, but it's going to be something that fits in a 64-bit RAX. If you invoke exit, or exit from a thread pool, that will never return, obviously. Okay. To understand the assembly program, you have to be very conscious of the size and representation of the data. Keeping track of whether you want this to be a signed or unsigned number, very important. Let's go back to writing assembly, and let's write hello world. Here is our hello world program. Now, we use syscall to write out hello world, and we use syscall to exit. All this does is write out hello world and then exit. But there's still quite a bit going on. Let's walk through it piece by piece. There's some data, and if you look at the bottom, we'll see in fact there is a .data section. We're going to cover sections in just a moment. But for right now, just remember that .data holds initialized data, typically read-only data. And a different section, typically BSS, or block started by symbol, don't get me started on that, historical name, BSS holds uninitialized data that's readable and writable. So it's like a little readable, writable pool for your program. So within data, we have a couple of things defined. The first, we have a label, message, and that label gives us the first byte here, which holds a capital H. DB introduces a series of data bytes, and we can give them in a few different forms. Here we give a few that are ASCII bytes in quotation marks, and then we give a 10 over here on the end, and that 10 is a new line. All right, 10 is the ASCII code for new line. So it's hello world, exclamation mark, new line. And the bytes that make that up are stored starting at the location given by message. We'll also need the length. How do we get that? Right? This is not a null terminated string. I didn't put a 0 on the end. I could have, but I didn't. So how do I know the length? Well, the $sign is the current address. So think of it as a special label that's always the current position within the assembly. And so I take the $sign, which is pointing right here just one past the 10. I subtract message, which points to the H, and that gives me the length. So $sign minus message is the length. And then I say len, another symbol I'm defining, is equal to $sign minus len. This is NASM syntax. Different assembler will have different syntax. DB, there's in NASM also a DW for data word and a DD for data double word, and I think a DQ for data quad word. Okay. Again, NASM specific stuff. Right? And there's the length calculation. Let's think about sections for a moment. So up here at the top, we declare some stuff, and we declare it to be part of section.text, right? So I give the directive section text. I say everything after this goes in section text, and I give some stuff. Then I say section data. Everything after this goes in section data, and I give some more stuff. So this goes in a section called text. This goes in a section called data. What's happening here? A section is just a logical grouping of a chunk of your program. And there are some common ones. And the common ones have defaults about their access. So if I say .text, then everyone's going to know that I mean executable but not writable. If I say .data, everyone's going to know I mean read-only. If I say BSS, everyone's going to know I mean writable and probably not initialized. And RO data is just basically another section for read-only data. These are common names that you'll see a lot. They're recognized by NASM and other tools. And so when NASM sees .text, it assumes executable but not writable. Okay? When it sees .data, it assumes not executable, not writable. So it'll have assumptions associated with them. But you can name them anything you want. So here, I just changed the names. So up here at the top, you'll see I have a section called stuff. and I set it to be executable and to be aligned on a 16-byte boundary. That's a good idea. It turns out, we'll talk about why later on, but I like it to be aligned. So sections is called stuff, and it's executable, and there we go. I put some stuff in it. All right. Then down here I have more stuff. I mark it as not executable and not writable, and I put my data in it. And then down here at the bottom I have another section stuff with the rest of my program in it. Wait a minute, I put the data in the middle of my program. How's that going to work? Well, the sections get concatenated together. So up here, this is part of section stuff, and down here, this is part of section stuff. And they just sort of run together. So this will be put in, it'll skip over that at the different section, and it'll put this in. So section stuff will contain the top stuff and the bottom stuff. And then section more stuff will just contain this. So I still have just two sections. One holds my data, one holds my program. Pretty easy. I did have to be explicit about the access rules for each one because I'm not using one of the default understood names. And if you want to see the effect of that, you can do things like change these, remove exec from here, and see what happens when you try to assemble it. We can see the sections using objdump. So I do objdump-h, which shows me the section headers, and -w, which makes it wide. And I'll see there are, in fact, two sections in my assembled file, stuff and more stuff. And I can see what they are. Stuff has code in it, so it's executable. It's read-only, and it wants to be allocated. More stuff has data in it, and it's read-only, and it wants to be allocated. I can see the file offset of each one. I can see the size, right? There's just 14 bytes and more stuff. And I can see the alignment. I told it I wanted stuff aligned on a 16-byte boundary. That is 2 to the 4th. So there's the length. There's the offset into hello.o where the contents are found. I could use XXD to just look at those bytes. There's the alignment, and there are the flags. Now, if I fully compile it, so I compile it and then I link it, I'll see the same kind of thing, except that back here, you'll notice I had this weird relock flag, and then it's gone. We'll talk about relocations later on in the semester. You'll also notice I filled in this. This was all zeros before. Now it's got some numbers in it. Let's go back a bit. Right? All zeros here. We didn't know what the virtual memory address or the load memory address were. Now we know what they are, and they're the same. Right? The virtual memory address is going to be the address of this thing when it's loaded into memory for running. Except not really, because of something called address space layout randomization. But don't worry about that for right now. The LMA is nearly always the same as the VMA, except in certain cases when you're building a ROM, for instance, they may be different. But for our purposes, they'll always be the same. Let's talk about the entry point. So up here at the top, I have global start. And then I have start. This is the entry point for the linker. The linker knows that this is where I should start executing the program. I could have had code above this, and then start would be here, and it would ignore that, and it would still start here. And I have to mark it as global. I can change the name of the entry point. So I can instead, I could say global first. And then I say first here. If I do that, the linker is not going to know where to find it. So I have to tell the linker what my entry point is. I can do that with -e and give it the entry point. If I'm building a linker script, which is way beyond this class, I would do it with entry and then the symbol. So entry first would be in my linker script. The linker is a complicated beast. So the entry point can be spotted if we dump out the information on hello. So I get the fully assembled and linked hello, and I do an objdump-f, and I'll see some information about the file, including the entry point right here. This is the VMA of the entry point. And I could dump out the symbol table with objdump-t, and I'll see _start, and I'll see that its value, which is over here, is the address of the entry point. In fact, I'll sort of see all the labels in here, right? So here's my length of my string. That was 14, and sure enough over here I see an E, which is hex 14. I see my message address. I see done. I see hello.asm stored in here. It doesn't have a value over here. It's just a symbol in there as a marker, and some other stuff. All right, let's look at write. So the first thing we do in hello world is we write out hello world. That's it. That's what we're doing with hello world anyway. So we go look at Ryan Chapman's blog. We find out that hello world is 1, and it takes a series of arguments. We could also do that by looking at the man page for write. So that's section 2 of the man pages. So man to write will show us the entry for write, and we can get the prototype from it there. Now, I mentioned earlier that the first argument goes in RDI, the next in RSI, the next in RDX. And so the first one is the file descriptor. So I want to write the standard out, which is file descriptor 1. You may remember that from C. I don't know if they still teach you that in C, but they should. So file descriptor 1 is standard output. So I'll want to put 1 in RDI. And so that's what I do right there. The second argument is a pointer to the buffer. So I'll put that in RSI. And so you'll see here, I move message, whatever that address is, into RSI. And I use R because, again, 64-bit thing. That's the memory address. That has to be 64 bits. Finally, I need the count, the number of bytes to write out, and that goes in RDX. And sure enough, I put length in RDX, and then I do a syscall. So this sets up all the arguments. It tells me, this first thing tells me which one I want. These set up the 3 arguments. The syscall makes it happen. There's my syscall. After it's done, I'll get back a value in RAX, but I don't care. I'm going to ignore it. What about exit? Exit's done the same way. I can look it up, and I'll find out that from Ryan Chapman's blog that it's number 60. So I put 60 in RAX, and you'll see over here it has a single argument. First argument goes in RDI, second in RSI, third in RDI. There's only one, so that first argument, the status, goes in RDI. So I put 0 in RDI for a normal exit. And then I do a syscall, and it will never return. This syscall does not return. What happens when I do this exit, or when I do an exit from the thread pool, is the operating system removes my process from the scheduler. That means I don't get any more cycles. And then it deallocates my space. Well, I'm just done. My process is just gone, right? Like it was never there. So there's nothing after that. So why is there an instruction following the syscall? Why is there a halt? Well, that's a weird pro forma thing. That instruction should never execute. And you may be wondering, I hope you're wondering, what happens if that does execute? What does that do? Well, it halts the processor. Now, wait a minute. It halts the processor? That can't be right. It is. What happens when you run that instruction? Let's try it. I always believe in trying things. Here's some code with a little make line at the top. Section text, global start. There's our start, and we halt. And that's it. We can assemble that and link it. We can do it with make if you want to. And then we try running it, and we get a seg fault. That's because halt is a privileged instruction. And we are not the kernel, so we are not allowed to execute halt. We're not allowed to stop the processor for everybody. And that's a good thing, right? All right. So why do we have halt here? It's kind of a defensive programming thing. If we run into this, we'll get a seg fault, and it'll immediately stop our program, and then we can diagnose it. So sometimes you'll see halts in programs where things should never go. I've seen some code where we have, a branch condition, and then the opposite branch condition, and then a halt, which indicates, if somehow you manage to fall through those because of some weird internal race condition, it just stops the process. All right. With the great freedom of assembly language comes the responsibility of knowing too much about your program. Let's think about the stack and procedure calls. So what is the stack? Well, if we look at process memory, again, we've looked at this before, but let's take a closer look at it now that we have some more names we can put on things. We'll put high memory at the top and low memory down at the bottom. So address 0 is at the bottom, and then the highest address is up at the top. And we'll lay out our program's space. This is virtual space, right? So it looks to us like there's a real address space that has all these values in it, but in reality, there's just whatever actually gets allocated and mapped, right? We don't know the physical address of any of these. We just know we have some virtual addresses or VAs. So typically the first thing is our .text, which contains our unmodifiable program. Then there's .data, which contains our unmodifiable initialized data. Then there's BSS, block started by a symbol, which contains our modifiable but uninitialized data. This is just space we reserve, like scratch data, scratchpad data. Well, a fixed amount of workspace is fine for some programs, but other programs need to have more space because they don't know how much memory they need initially. And those will use malloc and other methods to reserve heap. And so up here is the heap. The heap can be thought of as a collection of memory, and the heap grows upward into free space. And again, the program break points to the first open spot after the heap. Up in high memory, there's the stack. And the stack grows down into free space. And the last thing pointed into is pointed to by RSP. So you can see how, again, all these things, there's a choice of here or here, here or here, I choose the higher address. Okay. So there's our space, and we see that sure enough there's this thing up at the top called the stack. So when an item is pushed onto the stack, the following things happen. The stack pointer is decremented. In other words, we subtract from it by the number of bytes, and then the value is copied into memory starting at the new stack pointer address. So the first thing we do when we push, EAX, that's 4 bytes, is we subtract 4. So the stack pointer was here, we went down 1, 2, 3, 4, so we're pointing here right now. And so the stack pointer decreased by 4. So let's watch that again, and you can see the little 8 become a 4. This is what's in EAX. This is what's on the stack. There's some stuff there because, it's not like those aren't bytes. Those are real bytes. The next thing we do is copy EAX into that space. And again, we're in a little Indian machine, so we're going to expect 70 to go at the lowest address, or right here, and then expect 73, then we'll expect 72, and then 24. Let's see what happens. That is, in fact, what happens. Okay, so we copy it in. Now, you'll notice over here, I gave you 2 instructions. These 2 instructions would do a copy into the stack. They would do the same thing as push, with one important exception. Push doesn't set any flags. This subtract does set flags. So we would set some flags. But this would have the same effect as a push. In fact, I could simulate a push by doing this, and that would work. Okay. What about when we want to pop a value? Well, we'd sort of do the opposite. The first thing to do is to copy these values out of the stack into the register. So we need to copy these bytes over into EBX, which currently holds this value. So we'll wind up with 24, 72, 73, 70 in EBX. Let's do that. Boom, there it is. The next thing to do is to increment the stack pointer by 4. 1, 2, 3, 4. So it points there. Let's do that. And here we are. Now, the values we'd stored did not go away. They're still there. We call this the dirty stack. These are values that are still stored on the stack and could still be accessed, right? If I again move the stack pointer down, those will be in here. Or I could just, ask what's in memory at stack pointer -4. That would work. It's accessible. Hopefully it doesn't contain like an encryption key or a password or something like that that I can exploit. And again, these are the instructions, right? And they're have exactly the same effect as the pop, except they take longer, and the add will set flags. The stack pointer is RSP. It always points to the low byte of the last item pushed. And here's an important thing to remember: subtract to reserve stack, add to release stack. All right? It seems like that's kind of backwards. Keep that in mind. Procedure calls. All right, now we're getting into some interesting stuff. Now that we've talked about the stack, let's actually talk about how we might use the stack. So there's an instruction called the call instruction, and here's what that does. It pushes the value of RIP onto the stack, and then it loads RIP with the argument to call. And that will be one of these cases. It could be an address contained in a register, in which case this value, if it was an RAX, is loaded into RIP. So this is basically push RIP and then move RIP comma RAX, except that neither one of those instructions will assemble. You have to use the call to have that same effect. I could do a call indirect. So what this does is this takes my base, adds RBX times 8, loads the contents out of memory at that location, and loads it into RIP after pushing RIP. This is a way to build jump tables, and we'll see that show up later. Or I could just call it by an offset, so I can compute the offset. Maybe I use the absolute value, but more likely I use the offset from RIP to read, and I'll call by offset. So call does that, pushes RIP, loads a new value in it, and that's all it does. That's it. What about the return? The return pops the top 64-bit value from the stack and loads it into RIP, and that's it. That's all it does. Now, if there's an argument with return, it does something a little different. It pops the top value off the stack, loads it into RIP, and then increments the stack by the argument. We may see an example of that later on, but for now, don't worry about that. Return is once it loads that value back in RIP, then you just continue going. Think about how this works. I've saved RIP, which points to the next linear instruction. I've jumped to another location, and then when I'm done, I load the old value back in RIP off the stack, and so now I start at that next linear instruction that I saved before. And that's it. There's not much of a mechanism in there. It doesn't save my registers. It doesn't do any of that stuff. Okay, there you go. So here's a program with a subroutine. And it's going to print out Hello World in a few different languages. So we got Hello World, Hola Mundo, and Hello Welt. And we're going to print those out. And so we have a little subroutine up here called print. And notice that this code occurs prior to _start. So it's important that I declare start here because I want to start here. I don't want to start up here. So I have a global start. Here's my start. And what am I going to do? I'm going to load the address of message 1 into RDI. Now, this is an important point. You may be tempted to say move RDI comma message 1, and that will work. But it is more common when writing assembly to do it this way, and there are good reasons to do it this way, which we'll talk about in the future. Okay, so I'll load the effective address of message 1 into RDI, and then I will call print. So RDI will hold the argument to print. Then I'll do it with message 2, and I'll do the same thing with message 3. Then when I'm done, I'll put 60 in EAX, which will 0 extend into RAX, so really I'm putting 60 in RAX just with fewer bytes. Then I will XOR EDI with itself. What? That will 0 out EDI. You can think about that for a few moments. We'll talk about some of these idioms more later. Then I'll do a syscall and halt. This will exit. And so what does my subroutine do? My subroutine puts EDX and EDX together and exclusive ORs them. That zeroes out EDX. Does it really? It does. Again, you have to think about this, but that's a common idiom. Then I decrement EDX, then I increment EDX. And why am I doing that? There's a trick to it. You can walk through this if you can figure it out. I then compare the byte pointed to at RDI is my argument, and RDX is what EDX is. So this was initially set to 0, right? Decrement, increment, we'll leave it at 0. I compare that to 0. And if it's not equal, I go to the top and increment it again. What this is secretly doing is counting the bytes until I hit the first null. I've got a null terminated string here. And this is finding the number of bytes in the string up to the first null. And so I wind up with the number in RDX, or EDX. I put 1 in EAX for write. I put RDI in RSI, that's the pointer to my string. I put 1 in EDI, that's my standard output. And the number of bytes to write is in EDX or RDX, and I got that up here. I do a syscall to write it out and return. Wow, that's a lot. So, and you can go through that here. Count the bytes to the null terminator, and then write it out. So note that I did in fact use LEA, and there you go. If I wanted to do it with move, I would just not have used the square brackets. I would have used move message 1 into RDI. So I can assemble it and then obj dump it. That's the command up here at the top. And this no show raw instruction doesn't show the bytes here, so it fits on the slide. And there's my stuff, right? There's print and print top, which if you remember back here was in fact an additional label I used for the top of a loop. And then here's my start, underscore start. So what happens when print is called? Let's look at the call and return and the stack. So call and ret and the stack. Here's a call. I'm calling 40100. What is that? That is this address right here, the start of my print function. So what is happening right here? Well, right here, RIP holds some value. What does it hold? Not this value. It holds this value, the address of the next linear instruction. Okay? So when we call this, we first push the current instruction pointer onto the stack. Here's the value of the current instruction pointer. We're going to push it onto the stack. Next, the argument to the call is loaded into the instruction pointer. That's this guy right here. So we're going to set the RIP to that. There we go. And now we're ready to run the print procedure. Now we're ready to return. RIP holds this value down at the end of print. And we're ready to return. And the top of the stack holds this value. We simply pop that value into RIP. There it is. There's the old dirty stack. And we resume right where we left off. We put our argument in RDI, but I mean, clearly we have to all agree on where arguments are going to be and where return values are going to be. That seems important. I mean, we need to agree if we're going to put stuff on the stack. We need to agree about the order of stuff on the stack. We need to agree who cleans up the stack. And, you know, if I'm using RAX and you're using RAX, we can clobber each other. So that's not good. We have to figure out how we can all live together and work together in this environment. And doing that is, we do that by convention, and that is called the calling convention. And it's, of course, a completely voluntary thing, right? You want to be a good citizen and play well with others, you follow the calling convention. Nothing makes you do it, right? If you don't follow it, you might skate by and get lucky, or you might get a seg fault, or some other terrible thing might happen. Anything can happen. So one way to do things is to put the arguments on the stack and store the return value in EAX. And this is a pretty common convention for a long time. on the 32-bit x86, and it's the cdecl calling convention. So I put my arguments on the stack. The return value is going to be an EAX, and there we go. But now, wait, and who cleans the stack up? There's stuff on the stack. And wait, when I call, the return address gets pushed on the stack as well. So how do I get to my arguments? Well, it turns out there's the callee is going to clean the stack up using a special version of the return, which has an argument. We've mentioned this a couple of times already. When you see that, you'll know that you're probably using the cdecl calling convention. So you might see something like this. The agreed way to put arguments on the stack is right to left. So we'll push arg3 first, then we'll push arg2, then we'll push arg1, then we'll call the subroutine. Now look where we are. The return address is now basically blocking our arguments, so we have to reach past the return address to get to our arguments. And we do that. We're typically in a 32-bit world, so the return address will be 32 bits. And so we have to reach back 4 bytes past this to get here. So we look at ESP plus 4, that's arg1. ESP plus 8 is arg2, and ESP plus 12 is arg3. Notice how the ordering works out beautifully, right? We expect arg1 to be the first thing, and it's at the lowest address. arg2 is at the next. arg3 is at the next. Works out very nicely. That's why you push them sort of in the backward order. Now in return, the subroutine can use the instruction ret12 to free the 3 arguments. So return is going to pull the return address out here. That comes off the stack regardless. And then I give it an argument. Implicitly it's 0, but I can give it an additional number of bytes to deallocate. In this case, I want to remove these 4, and these 4, or these 12 from the stack, and so I'd use ret12. So there we go. The downside to this approach works well, worked well for a long time, is that it potentially requires memory reads and writes, and they're slow. Now that's probably going to be cached. It might even be locally cached in a clever way on the processor, but it might not. So another way to do that is to put the arguments in registers. Because one of the first things we're going to want to do anyway is take the things off the stack and put them in registers. So let's skip the middleman. Let's get putting the stuff on the stack. Let's get putting registers on the stack and then putting stack back in registers. And let's just keep things in the registers. Okay? So we'll put the arguments in the registers, right? Just like we do for syscalls. And then if we run out of registers, we can always put stuff on the stack, right? It's a last resort. Great. So here is a piece of the AMD 64 calling convention. There's actually more to the calling convention than this. It specifies things like relocations. We won't get into that for a while. Don't worry about it. This is a really important table. So you need to be sure you make a copy of this, save it somewhere, whatever you want to do. You need this table. It's very important. This is the AMD 64 calling convention. And you can see registers listed here with percents because it's AT&T syntax. Sorry, just live with it. And over here you'll find out what they're typically used for and whether they are preserved across function calls. Now, that doesn't mean they are. That means they should be. An important point. If I'm writing code, if I'm writing a function that's going to be called, this tells me whether or not I should preserve that value across the function call. So let's pick one. Let's pick this one down here. R11. Do I need to use, if I'm going to use R11 in my code, do I need to preserve its value? And the answer is no, I don't. I can go ahead and just write to it and not worry about anyone expecting me to preserve the value. What about R12, the very next one? No, I have to preserve that. If I'm going to use R12, I need to save its value somehow and then restore it before I return. Typically, I would push it, and then right before I return, I would pop it. Okay. You gotta keep track of all of this. Okay? It's important. Where do my arguments go? Well, it would make sense to put like one in RAX, the next one in RBX, then RCX and RDX. That's not how it works. The first argument's in RDI, second one in RSI, third one in RDX, fourth one in RCX, fifth one in R8, sixth one in R9. What about the seventh one? If it's a pointer or a integer, they have to go on the stack because I've run out of pointer/integer registers. What about floating point numbers? I don't put them in here. If it's a floating point, it goes in the XMM registers in order. Okay. What about return value? It's in RAX and possibly in RDX. RAX and RDX occur together in a lot of places. And here, if I have to return a 128-bit value, I'll use both RAX and RDX. All right. You can get a quick link to that right here. Almost everybody uses this calling convention. Linux, macOS, Solaris, they all use this calling convention. Who doesn't? Microsoft. They have their own. There's a link for that down there. Because Microsoft is on the board of the UEFI, the firmware on your computer also uses Microsoft's calling convention because they're on the board and they get to push that. Everywhere else you'll see the AMD64 calling convention. Here's a TLDR of it. Integer and pointer go in these, in order. Except system calls, where instead of RCX, you use R10. Floating point arguments go in these, in order. If you have other arguments beyond those, you push them on the stack. Return values in RAX. If it's a integer or a number, maybe it's an RDX too, and it's an XMM if it's a floating point number, or YMM or ZMM. Okay. So one thing you might be interested in here is, what if my first argument is an integer, my second's a floating point, and my third is an integer? Well, then it's RDI, XMM0, RSI. Well, you know, how do I know that? Well, you don't. You, the caller and the callee, just have to agree, right, that this is how stuff's going to be done. And that's what we've all agreed on. Okay. You must make sure you either do not modify or you save and restore RBP, RBX, 12, 13, 14, 15, and the stack pointer. Always preserve the stack pointer. All right. Here's an example using the calling convention. Here's a function. In this case, our function returns its argument. That's all it does. What does the compiler make of it? It makes this. The compiler says, okay, here's what I'm going to do. I'm going to output this branch protection thing. That is essentially a no-op. It's used by the branch protection system. We'll cover it at some point. For now, don't worry about it. It has these 4 opcodes, and that's it. If we compile it with Clang, we don't get that. So I wouldn't worry too much about it. It's not significant. What do we get down here at the bottom? Well, we get push RBP, and then at the bottom we get pop RBP. Why is that? RBP is a callee saved register. Preserved across function calls? Yes. That means we are required to preserve its value. We have to be sure that the value it came in with is the value it leaves with. And we might use it. And if we use it, we got to put it back the way we found it. Right? This is the Boy Scout rule. Right? You're going to leave nothing behind you. Fine. We notice that's also the case for the stack pointer. We need to preserve the stack pointer. Well, we typically do that by storing the stack pointer in RBP. Well, that means we're going to write to RBP, which means we have to save it. So you'll almost always see a preamble to a function that begins push RBP move RSP into RBP. You'll see that. That's so common, just expect to see it. At the bottom, you'll often see the opposite. Put RBP in RSP and then pop RBP. We never modified the stack in here. Neither one of these instructions modifies the stack, so we don't have to restore it. And so that got optimized away, and we're done. Okay. We don't have to do any of this. We could not do this. Nothing's going to punish us if we don't. If I'm doing this because, see, the code here actually references stuff on the stack. But if I didn't, I wouldn't need any of this, and I could not have any of it. All right. Just a convention. Again, we save the stack pointer. The current value in RSP, and which is now in RBP here, is the address of the lowest byte of the return address. And we don't want to overwrite that. Okay? Our stack begins just past that location at RBP -1. That's stack we can use. RBP and above is not stack we can use. This points to the end of our stack frame. Our stack frame ends at RBP because if we move beyond that, we are messing with stuff that we probably shouldn't mess with. There might be arguments for us up at that point. We can read them, but we never want to write to that space. There are also enter and leave instructions. And these are synonyms for that preamble and that exit. The leave instruction you'll see quite frequently. Sometimes you'll see pop RBP, sometimes you'll see leave. Leave is exactly a synonym for those two instructions. Leave does those two things. You can have those two, you can have leave, it doesn't matter. Enter is kind of a synonym for the other stuff, but it also lets you reserve stack, and it's got some handling of special cases. As a result, it's slow, so nobody uses it, or very rarely is it used. It's almost never used. I scanned all the ELF binaries on my system. I found 15,000 instances of enter, mainly occurring in the same program, and 192,000 instances of leave. Okay. So they are both used. You should be aware of what they are, but leave is used much more than enter. They don't occur in pairs, right? Most people will do this 2 instruction preamble and then call leave at the end. A scan of Python 3 shows no instances of either one. They didn't show up in the current binary for Python 3. So I'll try to use both over the course of the class just so you get used to seeing them. There's something called the red zone. That occurs when the offensive team gets within 10 yards of the... wait, I'm thinking about the wrong red zone. That occurs when you are within the 128 bytes of the stack pointer, the stack frame that you came in with. So remember, RBP is the base of our stack frame. The low 128 bytes below that are considered the red zone. And what that means is we can use those without allocating them, provided we don't call anybody else. So the way of saying my function doesn't call any other functions is to say my function is a leaf function. I'm not calling any other functions. If I call any other functions, the return address gets pushed on the stack, right? That might overwrite something in that 128 byte zone. But if I don't call anything, I don't need to do any allocation to use those 128 bytes. Specifically, what it says is if an interrupt handler or something else jumps in and takes over the machine for a moment to do something, it promises not to write to those bytes. Okay? This actually is an optimization thing. This means that my little leaf function doesn't have to do anything to the stack. It can just do some stuff in memory and then just be done and use that 128 bytes as scratch memory to do its work. And that can potentially speed up these little leaf functions that are used a lot and make them run faster. Okay, so There we go, red zone. I'm not going to talk about it much. It doesn't show up that much, but sometimes you'll see people manipulating the stack in this space without having first reserved it, and that's because of this red zone. Local variables. It's common to store local variables on the stack. For instance, you might want to store some 8-byte value on the stack, and you can do it with assembly that looks like this. So I go ahead and I can reserve some stack space. So I reserve stack space by subtracting from RSP, right? Remember, high address up at the top. I'm moving down, and so I subtract and move the stack pointer down further, and that leaves a gap, and I can then use that gap. So in this case, I reserved space for 4 8-byte values. So I subtracted 8 times 4 from RSP. And NASM will figure this out and substitute a constant literal in here, in this case 32. This is just a fancy way of writing sub RSP 32, which gives me space for 4 8-byte values, or 8 4-byte values. And now I can access them by using RBP. So think about what happened here. I moved the stack pointer, but RBP still holds the top of my stack frame. And so I would access the first one by RBP minus 8, the next one by RBP minus 16, RBP minus 24, and RBP minus 32. That makes sense? Our function uses one local variable, and it uses that local variable in the red zone. So we're getting to see both things happen here. We're using the red zone. We didn't allocate any stack, but we're actually referencing it below the stack pointer. So we're talking about the red zone here. In this case, we take RDI, which is, remember the calling convention, the first, and in this case, only argument to our function. We're storing it in this little temporary place as a temporary local variable. We don't do anything with it, so the next thing we have to do is put it into the return value. So I go and get the contents of memory out of the red zone, I put it in RAX, which is my return value by the calling convention, and I return. Wow, that seemed unnecessarily complex. Well, that's sometimes that's what you get. Optimization would probably clean that up a bit, but you can sort of see all the different little pieces of that in this super simple function that just returns its argument. Okay? So there we go. Since our function just returns its argument, we could have replaced all of this. Right? All this did was move RDI in here, and then from here into RAX. We just moved RDI into RAX through an intermediate variable that we didn't need to have. We could have just done this, move RDI into RAX, and that would be fine. So let's optimize our function and see what we get. So now I compile it with an optimization flag -O2, which says do some optimization, and I dump it out, and look what I get. I get my branch marker and my return, and then I get the one instruction here. So there we go. Optimization gave us exactly what we expected. The nice thing about this is it gives us something for a debugger to look at. So a debugger can go and look at what's in these intermediate values in memory, right? It doesn't necessarily know what's going to be in a particular register at a given time. If I have a variable X in my program, and that's always stored in some register, but it might change which register it's stored in, it's hard for the debugger to figure that out. Whereas if X is in memory, in some temporary value in memory, then it's easy for the debugger to figure it out. That's why debugging is often distinct from optimization, because optimization might destroy information a debugger needs, like these intermediate values. All right, enough of that. Nearly everything is by convention, and there are many different options. And if you want to use other people's code, you've got to follow the same calling convention. You've got to agree on how you're going to do things. Or don't. You can break the calling convention and see what happens. What happens if I don't do what I'm supposed to? Right? Conventions are often assumed, and vulnerabilities often happen when there are unenforced but assumed conventions. So you should always watch for that. Homework 2 is going to be due on the 7th of September. And it is to compute something called the Hamming distance. This is a very common calculation that occurs in a lot of areas. Cryptography is one. Suppose Alice sends this message. So here's some bits. And Bob receives this message. Well, these two messages aren't quite the same, right? These are the same, but Alice sent a 1 here, but Bob erroneously got a 0. And then down here, she sent 2 1s, but Bob got 0s. So there were 3 errors introduced in this transmission. Hamming distance counts those errors. One way to do that is this code over here. So what's happening over here? I give it two 64-bit values. I initialize my distance to 0, and then I walk over them. I run 64 times. Each time I check the last bit to see if it's the same. And if they're not the same, I count 1 to the distance. I shift them both right by 1, which drops off that little bit. And I just do that 64 times, comparing every bit and summing them up, and I return the distance. There are many ways to do that. This is not a particularly fast or clever way, but it will work. You might see if you can find a faster algorithm, but you don't necessarily have to. Okay, just turning that into assembly would be great. Okay, once you've turned it into assembly, here's a little program you can use to check it. So notice that I have this function prototype at the top. It takes two 64-bit values and it returns some result called Hamming. And there's no definition for it because you're going to provide that in your assembly. So how are you going to do that? Well, here's the make line at the top. It's going to first make something called Hamming.asm, which will give you a Hamming.o, and then it will compile and link with this file, whatever you want to call it. What about the return value? Here I say 16. How do I specify that? You don't. You just return REX. And the compiler will know that, that should be this, but don't worry about it. Just return REX. Here's a template for your code. This is what your code should look like. You're going to have a label Hamming, which is the start of your code, and it's going to have to make that global because you'll want to link with it. So it has to be global. Here's that preamble. Here's the exit. Within here, your code has to figure out the distance between the two 64-bit values, which by the calling convention, first argument here, second argument here. Return value needs to be in RAX. Do all of that and you're good. Okay? What is this? We'll talk about that another time. That's just there so that you don't get an error when you link. That's it.